Okay, let's continue with relative motion analysis. So last time we explained about the three vector. So one is translating, one is moving, one is fixed. So we have one fixed x and y, and then one moving axis, which labeled as y, comma, x, comma. Yeah. Okay, this one already done. So this one also we explain how to get the vector position. You can start with RB stroke A. So you just convert the slash become negative. It depends on the question. Sometimes is from, we will pick one of the 2 points B from the body. So looking towards B point on the same body. So we have B stroke A means position to B from A. Okay. Okay, now we have a scenario where there's a motion. So on the left, it's a starting position in this position. And then after a certain time, you see the body switch to another position like what you see on the screen here. Okay, and this one, you know that it is involved two translation and then one rotation. Okay, so the combination of these two become general plane. Okay, so you can imagine how to move from the left diagram to the right diagram. It must be have one translation and then turning or rotation to this position. Okay, it's a combination. So we try to break this diagram into two motion. Okay, so before we break the motion, so we have to identify the displacement A to A, means from the left to right. We label the changing of position A to A is DRA, and B to B we have DRB. However, the RB stroke A always the same because the 2 points like your head and your toe is always the same distance, right? We label the direction of where you see A to B, you write RB stroke A. So it's the same on the left hand side, right hand side. Okay. So what is important is we want to use calculation to define the dynamic motion of the body, the general plane motion. Okay. So we can break the motion like what you see on the left hand side, where there's a two motion. One is A to A, means you imagine this one as a stick. It moves like this. First is move translation, linear translation in a straight line. So A to A point, B to B point, B in the center here. So, or you can see as a dotted line here. This position is translation. And then to meet the final position, you need to rotate around A. You need to rotate the dotted line to this position. Make sense, huh? We have two motion, translation and then rotation. So this motion first, and then we start to put in the notation of the diagram. Just now we already have DRA, but translation one, the first translation, you have the same distance from A to A, B to B to the dot DRA, and the same DRA is the same vector, the same direction, parallel, have a linear translation. From A to this B comma, the same distance as RB stroke A. So you copy RB stroke A to here. It's the same. Yeah, so the first motion is translation, linear translation. Then we move on to second motion, which is rotation around A. So rotation, you always see as a circular motion. So circular motion, this is a section of the circle. It's a second pizza or pie section. So pie section, you know that S equal to R theta. S, the small section, equal to R theta in radian. Okay, so here from B comma to B, we have DRB stroke A, means from B to A. This one we have a small section here, is rotation for DRB stroke A. So it means from B to A rotation. This one. Then the theta is from rotation center at A. So the theta here. So we have two. One is translation, one is rotation. Then we start to build equation. Start with equation. Okay. This one you already know. So we know the motion, how it moves. Okay, now we start with the first equation. We start with the displacement. Identify. This one, we know that R, B, comma, and B, this triangular, we know that this is a rotation motion. So rotation motion, we see it as a section of the circle. So you know that how to calculate the section of the circle, you get S equal to R theta. S equal to R theta. So we can write DRB stroke A, which is the S section here. S section here, this one is S section, equal to R. Your R is RB stroke A. Theta is this theta. Yeah, we are using this formula, this section. This section, this is S, this is theta, this is R. So we use circumference or radian section formula, R theta. Okay, so this is actually is a section. This is a small section here. So this is your S, but this is because this is very, very small, so we can represent as a straight line. Because this S here is very, very small, so we can see as a, we can assume it as a straight line. Okay, so this DRB stroke A is S, RB stroke A is R, and theta. This is a small theta. Yeah, so it's a side-by-side comparison. Okay. Now we continue to establish. So the rotation DRB stroke A will be established. Then we look at the displacement move from here to here and to here. So there's a triangular here, vector triangular here. So B, comma, B. So you have three arrow. One is the first arrow is B, comma, and B, comma to B, and then B to B. You have three arrow that construct the vector diagram. You know that DRB, this one, is the resultant. Resultant is a product of addition of two vector, which is from here to here and here to here. So your vector, this one, DRB equal to DRA plus DRB stroke A. Okay, so this is the vector diagram of this one. Okay, so what are these three terms? On the left, DRE, this is due to the general plane motion. It's a combination of translation and rotation. From this position, we actually experience two motion, translation and rotation, which is on the left. And then DRA, this one is translation motion, DR, plus DRB stroke A, this is rotation from B, comma to B. Yeah. Okay, so we have established already displacement or position that you learned. So you can establish or you can develop velocity equation from displacement, which is you time differentiate it. So you have a position, ds dt, you get velocity. However, this is a rigid body and with a rotation. So you just put the equation 1 and then dt it. So we have all the dot lah, r dot, r dot, r dot. Okay. So you have this equation. So you take the previous equation and then you time differentiate. So you drb dt equal to dra dt and drb stroke a dt, because you want to find velocity of the motion. Huh? Okay, now why we use r in this context? Because we involve rotation, and it's a rigid body question. If it's a particular one dot, then you use s. But if it's a rigid body, you cannot use s anymore. So you can simplify your equation, or you can memorize it as VA equal to VB equal to VA plus VA stroke B. Or you can just remember, if you want to find VB stroke A equal to BB minus A, it depends on how you memorize. Okay. So this is just a vector that from the vector diagram. Okay, so from here to here, actually just change the R become V. Change the position to become velocity. Apply the same for acceleration. Acceleration also same. So this one will be AB equal to AA plus AB stroke A. It will be the same. Okay. So same. You just need to know lah. VB is this velocity. So velocity of B will equal to VA, velocity of A plus the velocity from A. So this is another mathematic derivation for this term. For this term, this is due to rotation of this A, B, comma to B, this rotation. Okay, this dotted line to this solid line on the left, on the right. So we are now focusing on the third term here, drb stroke A over dt. So we can rewrite this drb stroke A dt equal to r d theta dt. R d theta dt, how this come from? What is, okay, this term, RB stroke A is where? Is here. Again, this is a small section just now. So RB stroke A is your S. This is R, this is theta. S equal to R theta. So it's the same. So how to get your, this is the S. RB stroke A is the S, equal to R theta, right? So what is your R? R is this one, RB stroke A. Theta is this one. So you just replace your R as RB stroke A, and then theta is the d theta. You copy the dt to the right. Yeah, it's just that because later I want to transform this d theta dt to another term. Yeah. Okay, so we have, then we can rewrite this one. The d theta dt actually is what we know as omega, what we learned in previous section. Okay, so you can write the drb stroke dt is rb stroke A omega. You want to put this term back to this equation here. Okay, so VBA, or this one, dr d theta equal to this one. So if you want to find VB stroke A, you want to find this, the third term, VB stroke A, velocity relative position of B to A, we can write as omega R B stroke A, or V equal to omega R. But the V stroke A, B stroke A, you do the same. I mean, you refer to the same position, B stroke A, B stroke A. It's the same, right? So in a test, I won't ask you to derive this one. I just ask you to memorize V equal to omega R. And then this one is based on the diagram that you draw from the free body diagram. Okay, this slide, what is important is V equal to omega R. Okay. Okay, now we go into the motion of the rod here. So if this rod rotate clockwise in the motion, rotate clockwise, so you know that this one is when you rotate is a circular motion for both A and B. If you rotate this rod, point A will rotate in the circular motion, B will rotate in the circular motion. So when you have circular motion, you are moving in the curve, your velocity always tangent to the curve. So VTA and VBA. And then you have the omega. Omega is a rotational velocity or angular velocity. Yeah? So here, if you have a general plane of rotation and moving somewhere else, you have a combination of translation plus rotation. Okay, so we have two vectors. One is VA. VA will same as VB in translation because both move in the parallel line, the straight line. So VA will same as VB or VB will same as VA. It's the same. Then just now, if you have a rotation, yeah, if you move in the translation, there's no omega. There's no rotation. Omega 0 in the translation motion. Okay, so you have omega on the rotation part. Then you have a relative from A to B. So you write position of B referring to A, B, RB stroke A. And then the relative velocity of B to A, B from A is pointing this way. It's pointing this way and not this way because of the rotation anti-clockwise. Clockwise. So when you rotate clockwise, this one move in a circular motion. Velocity is always tangent to the curve of the motion. So velocity is pointing to the left and not to the right. So this vector is actually velocity of point B following the omega direction. And V equal to omega R. That is what important for rotational motion. Yeah. So when you have a general plane, you need to imagine how it rotates. How it rotates. Usually you have a general plane. It will consist of translation plus rotation. This one usually happen in a piston engine. Piston engine. Okay, so this one is just a vector diagram of the two. So this one you can see in the previous slides. Okay. So how to extract VA? VA you extract from the diagram, translation diagram. This one is moving to the right, so you copy the direction. What about VB? VB you copy from this diagram. It always tangent to the curve, 90 degree. So VB to the right. Or you can copy from the question. Copy from this direction. So you have VA, VB, and then you sure will need to have a resultant force. So resultant force, it depends on the question. In this question, in this setting, you're looking from A to B. From the body, you're routing from A to B. So you copy the vector B to A with this one. So you copy this one, put here. So the rest you read, or in vector form, you always have v equal to omega r, but it's a cross product in a vector calculation. It's always omega cross r. Okay, b stroke a equal to omega cross r. So the rest is just vector analysis. So you can write your equation if you see a rigid body that's rotating and you need to calculate velocity. This is what you write. You write VB equal to VA plus omega cross R. Okay, so this is the first equation. If you see some body that is rotating. Okay. Okay, the rest you read. So we apply what we learned. There's only this equation. We are applying this equation. VB equal to VA plus omega cross R. So this tutorial question, you just observe what actually is a bit different from particles. Okay, so you look at the question, you have a body of rotating and moving. So this one moved down, point A moved down, and it was limited to only vertical motion. So B also same, moving in the vertical motion. And this one is in the right angle. The A is moving down, Y down, and this one moving to the right, left or right in point B. Okay. And the point of A to B, actually, if you move A down, it's going to rotate the body. If you move A down, you're going to rotate the body. Point B, you're moving to the right. If you point A move down, A to B will rotate, and then B will move to the right. So the question asks you, if the velocity of A is given downward, find the velocity of B when your angle from the wall here reach 45. Okay, so before start, this one is B will be here, A will be on the top, right? So what you do, there are two ways, there are two solutions here. So first, this is the motion that you should know lah. So where is the motion? A move down, B move to the right, and so on. And then this cause link to rotate anti-clockwise. It will rotate like this, anti-clockwise, right? So your omega is like this now. So you're using right hand rules. Right hand rules, your thumb is pointing outward. Okay. So you're expecting, if you pull this rod out, you're expecting the motions happening like this, right? Your Y is pointing up, X to the right. This is your general axis. Y going up, X to the right. And then you have omega, which is anti-clockwise. A straight away move down, 2 meters per second. B, VB, you don't know. But you know VB, it must move to the right. So your answer in your analysis, VB should be positive, according to your diagram. Okay, if you calculate, your VB negative means something wrong in your calculation. Okay, so we do vector analysis using this diagram. You can break it into X and Y or IJK in vector form. Okay, so this is a direct application of VB equal to VA plus omega cross R stretch B. So we don't know VB. We have VA and we have RB stroke A, and we don't know omega. So since we don't have VB, we don't have omega, we need two equations. So where do we find the two equations? Is from the hints here, the X and Y direction. The hint is from the X and Y direction. So it means you break this equation into X and Y direction, then you have two equations, then you can solve two unknown. First equation in X direction, X equation in vector form, X is in the I direction. So you write VBI equal to VAI. VAI is what? VAI is, VAI 0. But VA you convert into a vector form. Going down Y is J, but you positive direction go up positive. However, your motion A go down, so you should write negative 2J. Yeah, this VA according to this diagram move down, but your axis Y positive go up, so your VA will be negative 2J. And then bracket omega. Where is your omega? You know that this is rotate like this, and you are using right hand rules. So when you point outside the sheet of paper, omega is positive K, because it's following your right hand rules. It's agree with your right hand rules. So positive direction. Okay. Yeah. So as long as agree with your right hand, you get positive term here. Positive that omega. Okay. What is your R? RB stroke A. RB stroke A is this one. This slanted A to B. So you have a angle of 45 degree here. So actually you have a right angled triangular. So right angled triangular, you can break this vector. Okay, this vector pointing to the B. So RB stroke A, this vector, you can break into x-axis and y-axis. Yeah. You can break this vector into this vector and this vector. So this vector, you have 45 here. So you have your resultant. So to find this one, x is sine. To find your y, to find the x, you should use cos. To use y, you should use sine. Okay, so this is 90 degree. 90 degree. So your RB stroke A in x direction is RB stroke A sine 45. It is this direction. Okay, R sine 45. This one is R cos 45. So why this one negative? Because you are pointing down and your positive direction is Y going up. So you're changing this RB stroke A into I and J form. And then you start to do cross products. Cross product this one you need to go back to vector appendix. I, J, K. I cross J, you get K. J cross K, you get -1, negative I, and so on. So K, W, omega K cross I, R cross I, you get J. And then K cross J, you get I. Yeah. K cross J, you get I. Then K cross I, you get J. So this one is the product of I cross I, what you get, I cross J, what you get, I cross K, what you get, and so on. I cross I 0. I cross I 0. I dot I is -1. Okay, so don't confuse with the dot product and cross products. Okay, so we are having a cross products, but this one you go back to vector. This is more mathematics. Important is today what we learn is VB equal to VA plus omega cross R. This is what we focus . So when you solve the problems, you look at x direction and y direction. So VBI in x direction, J is not our concern. J is not our concern. VBI equal to 0.2 omega cos 45I. So you have VB equal to 0.2 omega cos 45. And on the left hand side, we don't have J, so 0. Okay, VBJ is 0 because B do not go down. B only log to x direction. So J is 0. Okay, B 0. And then this one you copy. -2 plus 0.2 omega sine 45. You solve this one first. You solve the second equation, you get omega. Once you get omega, substitute back here, you get VB. Okay, so this is mathematics. So you solve for the second equation, you get omega. Once you get omega, substitute back here, you get VB. So this is how you solve for this question. Yeah, so in radian per second, and this one omega is according to your right hand rules. So it's clockwise and also to the motion of A. Okay, VB to the right. Or you can do it in a faster way where you use scalar analysis. What is scalar analysis? Means you just break it into a diagram form. So VB, VA, VB, and then you draw diagram. VB this direction, VA go down, omega, V equal to omega R, V equal to omega R, so omega R is fixed 0.2, but the direction is pointing 45 going that way. Yeah, this one. Then you break into x and y direction like just now. So this one equal to 0. Then this one break into x direction. So cos 45. And then you do another one in y direction. VB only work in x direction. So y 0. You copy negative because go down. This one you get sine 45. And you're arriving at the same equation like previous one. Okay. The hardest part, if you use this one, scalar analysis, is you very hard to imagine the direction of VB stroke A. This one. Because the question only stop here. You don't know the direction, whether it is, where does it go? Huh? But usually, VB of stroke A is 90 degree to the R. Usually, this one is tangent to the R. Because why? This one rotates circular motion. This one rotates circular motion. A to B rotates circular motion. So your VB always tangent to the curve. So you know this is 45. Yeah, always tangent. Okay, we have 3 more minutes. This one maybe become your homework. Okay, so something that rotate and then it asks you velocity of the point A. Conveyor, this one move, VC is given, and then omega rotate. So this one your homework. Go and see how it do. This for your homework. Okay. It was in the slides. So go home and read this one. Okay, so this one is another section. Another method of finding AR stroke IC, or from IC means from the instantaneous center, where you always have a 0 velocity. Okay, we have a centroid and you want to find VA and omega. This is another method of solving what you see previously. Another method where You go and find V. You have this point A on the body. Point in the body, and what this method is quite easy and the most simplest one. How to find? You have body rotating in this way. You know that your velocity always tangent to the curve. So you have VA already. What you do, you put your ruler. Your ruler have a sharp corner, right? You move your ruler to the point A. Then you draw a line along the ruler. You get one line called IC. This is 1 point. And we have 2 points. You do the same for B. Let's say your B is here. And it's rotate the same. So you have the curve like this. So you have VB like this. Then you use your ruler to draw a line. Use your ruler to go to that, and then your velocity like this. Then you have 2 intersection line. This is the centroid position. And then you can find the thing already. Okay. Okay, I think we stop here and continue tomorrow.